just start this recording here. Okay, so atoms, ions, and molecules. So chemistry is the study of matter, and matter is what makes up our universe. And so the main idea in chemistry is we want to understand the behavior of matter. Okay, and the way we do that in chemistry is we use the most fundamental assumption that it's made out of these little things that we call atoms, too small for us to see. Okay, but there's a lot of evidence that we can cite and explain in terms of the notion that matter is made up of atoms. Okay, so you could say that chemistry is the study of matter from an atomic perspective. Anytime you try to explain things, the way you see things you see around you in terms of what must be going on in the world of the atoms that make up that, then you're talking about chemistry. Okay. So what's an atom? Well, our current picture of what an atom looks like resembles what I have here in this figure. Okay. And so, in fact, we now know that atoms are made up of even smaller particles, which we call protons, neutrons, and electrons. And so, two of these types of particles, the protons and the neutrons, you find in a very tiny spot in the middle of the atom called the nucleus. Okay? So that's a very tiny spot in the middle of the atom, and going around very fast around that nucleus are the electrons. Now, electrons are very small and very, very fast compared to the protons and the neutrons, so it's frequently convenient to just imagine electrons as if it's like a cloud. It's like a blur around your nucleus. What do you see in between the particles, between the electrons and the nucleus? There's nothing. So the universe, we say, is just made up, as far as chemistry is concerned, it's just made up of atoms and the void. Okay, so in between those particles, yes? Okay. Okay, these down here, the two. Oh, you can't go full screen? All right. Okay, how's that now? All right. Okay. All right. So protons, neutrons, and protons and neutrons are collectively known as nucleons. Why do you think that's the word for protons and neutrons? Because they're found in the nucleus. So that's why they're called nucleons. The particles in the nucleus, the protons and the neutrons, are also collectively known as the nucleons. Okay? Now, just how small is the atom? Well, typical diameter of the nucleus is 10 to the negative 13 to 10 to the negative 14 meters. So that's 1 trillion, a tenth of a trillionth to 1 trillionth of a meter. And typical electron cloud, if you put the atoms as close as possible to each other, like if you put 3 neighboring atoms as close as possible, the diameter of the electron cloud would be about 10 to the negative 10 meters. So that's also known as 1 angstrom. Okay, so this letter right here with a circle on top is called an angstrom. That's 10 to the negative 10 meter, or that's equal to 0.1 nanometer. So nanometer, if you remember, nano means 10 to the negative 9. So if this thing right here, this diameter right here is 0.1 nanometer, or let's just call that 1 angstrom. Okay. And that diameter is 1 angstrom approximately, anywhere between 1 to 2 angstroms. So that means this nucleus to nucleus distance is about 1 angstrom, anywhere between 1 to 2 angstroms. That's as close as you can get the atoms to be in nature. Okay, so we say that half that distance would be the radius of the atom. Okay, And so that's typically where your electrons will be roaming around. The nucleus itself, you'll notice 10 to the negative 13 is 1,000 times smaller than 10 to the negative 10. So this little tiny spot right here, that diameter is only 1/1000 of the entire diameter of an atom. Now, since we live in a three-dimensional world, volume is length cubed. So you cube that 1,000, that's 10 to the third cubed. That's a billion times smaller. So you say that the amount of space occupied by your nucleus is at least a billion times smaller than the amount of space where that electron is roaming around. Now the electron itself is very, very small, even smaller than the nucleus, so pretty much you can say that an atom is mostly empty space. So most of the picture you see of atoms, visualization of atoms that you see is really distorted, and here's a website that explains more about that. The distortion has to do with the fact that it's just on that scale, it's just so hard to compare the nucleus to the region where the electron is moving around. So in a way, this thing right here is exaggerated. Okay, this obviously the nucleus that I've drawn here is obviously not 1,000 times smaller than the size of the atom itself. Okay, so when we talk about the size of the atom, we're talking about the region where you might find the nucleus roaming around. Most of that region where that electron is roaming around is in fact empty space. Okay? Now, protons and neutrons are in fact made up of even smaller particles called quarks. Okay? And leptons. And so in the so-called standard model of particle physics, all matter in our universe is said to be made up of quarks and leptons. There are 6 kinds of quarks, 6 kinds of leptons, and an electron is an example of a lepton. And so here's a website. If you want to learn more about that, it's called particleadventure.org/standardmodel.html. I think there's an underscore there. So if you're interested in that, you can learn more about that there. But as far as chemistry is concerned, we're not really going to be too much interested about quarks and leptons other than the electron, of course. And because for most of what we're dealing with in chemistry, we're really concerned about transformation of matter, converting one substance, one form of matter into another. And in those cases, we can understand things at the level of the atom, at the level. In fact, most of the time, we're just interested in the behavior of the electrons that are outside the nucleus. Okay, so they are roaming around the nucleus. Most of the time, we're not even concerned about what goes on in the nucleus. For most of what we see around us, the nucleus, in fact, remains intact. All right, so let's talk about matter in general. When we try to describe matter, we can use things like color, melting point, boiling point if it's a liquid. Those are things that we use to describe matter, what we call properties of matter. Okay, so a property is just something that we use to describe matter. So if we talk about your height, that's going to be one of your properties. Okay, kindling temperature, for example, the minimum temperature at which something burns, that's another property. Right? Now, most samples of matter that you find around you, okay, in the universe, in nature, can be separated into 2 or more components with different properties. And so one of the early preoccupations of chemists was to separate samples into different components, and so that you can get components that have different properties. Ultimately, though, if you keep doing that, you get to a point where you have a sample that you can no longer separate into 2 or more components that have different properties. So you might separate it into 2 parts, but those parts would have the same properties. At that point, you have what is called an element. So an element is a sample that you cannot separate into 2 or more components that have different properties. And at the atomic level, we interpret that to mean that that sample is made up of only one kind of atom. So the word element and atom tends to be synonymous. We say that a sample that's made up of only one kind of atom is a sample of a pure element. So if you have a sample that's made up of 2 or more kinds of atoms, then you say that that sample is made up of 2 or more kinds of elements. All right. So the protons. Differences in the properties of the elements are due to differences in atoms, we say. And it turns out that all atoms of the same element have the same number of protons. So in other words, the number of protons is an identifying number for atoms. All atoms that have the same number of protons are atoms of the same element. Okay? If we have two atoms and they have different numbers of protons, then they're atoms of different elements. We typically use the letter Z, capital Z, to specify as a symbol for the number of protons, and so, oops, hold up. Okay. And so the number of protons, which we call the atomic number, like I said, can be used as an identifying number for atoms and elements. Okay, and the elements that are known in nature are listed in, that we know so far, are listed in a chart called a periodic table in increasing atomic number from left to right. And here's an example of a periodic table. It's a good one to have, to print out, to have handy, because this one has a lot of information about the elements. This particular periodic table you can download from the NIST website. You can download a very high resolution color version of this colored periodic table. Okay, and so what you'll notice, the atomic numbers are listed here. There's 1, 2, 3, 4, 5. So it's listed in increasing atomic number, left to right, top to bottom. You'll see a break here, number 56. Okay, 57 is down here to 71, and then the numbering continues here at 72. And then down here you have 88. There's a break. Okay, it skips to 104 because 89 to 103 is down here. Okay, and so this is a periodic table that lists all the atoms that we know of. You'll notice here the elements that we find in nature as solids are color-coded. They're shown here in white. So most of the elements, if they were to find them in nature, most of them are solids. Okay, and then there are only two elements that are known to be liquids under ordinary conditions. If you find them in nature, that's mercury and bromine. And then the ones that are color-coded here in red, find them in nature as gases. Okay, so hydrogen, nitrogen, oxygen, fluorine, chlorine, and what we call the noble gases, you'll find them as gases in nature. And you'll notice here this yellow color coding. These represent elements that are not observed in nature. These are only elements that are created in the laboratory. So they're artificially prepared. Okay? So you'll notice each of these elements has a symbol. Okay, so for example, Ti right here is a symbol for an element called titanium. Okay, and so these symbols that you see here, you'll notice the first letter is always capitalized, and if there's a second or third letter, those are written in lowercase. Right? And so you need to know the names of all of these naturally occurring, names and symbols of all of these naturally occurring elements. Okay? So that should be part of your basic vocabulary. Here's the periodic table that you'll find on your test. This is the periodic table that you will have access to when taking any test in chemistry, and so at least in this class. And so you'll notice it just gives you the bare minimum. It gives you the atomic number, gives you the symbol, so you have to know what the name is. So if you see He, you should know what helium is. That's a symbol for an element called helium. Okay, and the other number that you see down here that has decimals in it, that's called the atomic mass, the average atomic mass, and we'll talk more about that later. Okay? All right. So remember we said that the number of protons is the atomic number. It tells you what the symbol of the element is and what type of atom it is. It's the identifying number for the atom. So let's answer this question. What's the symbol for an element whose atoms have 10 protons in their nucleus? Neon? Good. Very good. So the number 10 here, that's the atomic number. That means any atom of neon has 10 protons in its nucleus. Very good. All right. Atoms of an element may have different numbers of neutrons. So they must all have the same protons, but their neutrons may be, number of neutrons that they have may be different. So for example, an atom which we call oxygen 16, O-16, or you can put a 16 as a superscript to the left of the symbol for oxygen, is an atom that has 8 protons. How do we know it has 8 protons? We look at the periodic table and you see that the atomic number is 8. So if it's oxygen, you know automatically that it has 8 protons. And so if you have an atom that's called oxygen 16, that's 8 protons, so the remaining 8 plus 8 gives you 16. The other 8 nucleons must be neutrons. Okay? Oxygen 18, again, since it's oxygen, we know it should have 8 protons. And so in order to have a total of 18 nucleons, so that number that you cite after the symbol, or as a superscript behind the symbol, that's what we call the mass number. That's the number of nucleons. Okay? So oxygen 18 has 10 neutrons. So we say oxygen 16 and oxygen 18 are what we call isotopes of oxygen. As far as chemistry is concerned, pretty much they behave the same way. Okay, they're atoms of the same element. They're not exactly identical, but we say they're the same kind of atom. They're all oxygen atoms. They're isotopes of oxygen. Okay, neutrons are needed to stabilize a nucleus. So if you have too few or too many neutrons, you have an atom. That's what we call that we would call a radioactive atom. So what we know of as radioactivity is due to unstable nuclei. Okay. Of course, most of the atoms you encounter around you are stable atoms. Now, the typical abundance of the isotopes, you can look them up, okay, or you can determine that using an instrument called a mass spectrometer. So typical samples of matter that you find in nature, we say, are not isotopically pure. In other words, oxygen, if you find oxygen atoms in nature, okay, 7.57% of the time, the oxygen atom you'll find would be the oxygen 16 isotope. Okay, 0.038% of the oxygen atoms you find in nature is oxygen 17, and 0.205% would be oxygen 18. And these are things that you can experimentally determine in the lab using what's called a mass spectrometer. A good source of data for these isotopic abundance is a website called Web Elements. Let me show you that website, because it's a good source of information about the elements. So you just type webelements.com. Okay, why is my computer locked up? Webelements.com. So for example, if you click on this is webelements.com. If you click on oxygen right here, okay, gives you information about oxygen. So there's the name, symbol, atomic number. Okay, and over here on the left-hand side, you'll see nuclear properties, properties of the nucleus, right here. Okay, and under isotopes, you get the natural abundance of oxygen. So you'll notice it's 99.757% oxygen 16. Okay, and here's isotopic pattern. It's mostly oxygen 16. There's hardly any oxygen 17 and 18 in nature. Okay, and here are some examples of what we call radioisotopes, isotopes of oxygen that are unstable. Okay, and you'll notice here that you have the half-life for oxygen 14, for example, 70.6 seconds. In other words, if you have a way to create oxygen 14 in the lab, it will be gone in half of it will be gone in 70.6 seconds. All right. So that's how unstable it is. Oxygen 22 is a half-life of 2.2 seconds. 2.2 seconds after you create a bunch of oxygen 22 atoms, if you could do that in the lab, half of those would be gone. Another 2.2 seconds, another half of those would be gone. All right. So we'll talk more about these, what we call radioactive decays when we get to nuclear chemistry. But for most of chemistry, like I said, we typically don't deal with what happens at the nucleus. We're dealing with mostly stable atoms. The atoms we find in nature are mostly stable ones, the non-radioactive ones, and that's pretty much the focus of what we do in chemistry. All right. So what about the masses of these particles? Protons and neutrons have approximately the same mass. Each one of those is about 1,836 times more massive than electrons, about 2,000 times more massive than an electron. In other words, the nucleus carries most of the mass of the atom. So around the nucleus, there's hardly any mass at all. Those are the electrons. They hardly occupy any space. They just roam around that region around the nucleus in a blur, so we refer to that as an electron cloud. The mass of the atom is carried by the nucleus, which has the protons and the neutrons. So the actual masses of protons and neutrons are 1.6 times 10 to the negative 27 kilograms. You can see that's a very small number. So we can use what we call atomic units, and in atomic units, that's 1.0073 atomic mass units. So this U right here means atomic mass units. Sometimes it's abbreviated AMU, okay? And a neutron, you'll notice, is almost the same as a proton in terms of mass, 1.6749. So it's just these fourth and fifth significant figure that's different, or 1.0087 atomic mass units. So to three decimal places, three significant figures, both of these are 1.01 atomic mass units. So we can say, if you do just two sig figs, you can say they're both 1.0 atomic mass units. An electron, on the other hand, is 0.00091 times 10 to the negative 27 kilograms. So like I said, that's 2,000 times less massive than a proton or a neutron, 0.0005 atomic mass units. So if you were to round off the mass of your electron to the nearest hundredth of an atomic mass unit, what would it be? If you round up to the second decimal place, you can say, you can pretty much ignore the mass of the electron, okay? So mass of a proton, we say to one decimal place is 1. Okay, so proton mass, neutron mass is 1.0. And electron mass to the nearest tenth, in fact, to the nearest hundredth of an atomic mass unit is 0. All right, here's a clicker question. Which of these has the largest mass? 1 proton, 3 electrons, or 2 neutrons? So what's the popular answer? Eight people said C. Okay. So, all right. So 5 people picked A. All right. What's the mass of 1 proton? 1.0. All right. Atomic mass unit. 3 electrons. What's the mass? 3 times 0.0. That's 0. And 2 neutrons is 2 times 1.0. That's 2.0 atomic mass units. So the correct answer is C. 2 neutrons would have the largest mass among these. All right, now for very precise work, we cannot just add up the masses of electrons, protons, and neutrons to get the total mass of an atom. So for example, if you look at oxygen 18, it has 8 protons, 10 neutrons, and 8 electrons. It would seem logical that if you just add up all the masses of 8 protons, 10 neutrons, and 8 electrons, you get the total mass of the atom. Well, if you do it to the nearest tenth of a decimal place, tenth of an atomic mass unit, that's true. But if you really want to do precise, if you want to look at the precise number, okay, You can look up the mass of oxygen 18 atom. You'll find it's 17.991803. Obviously, what was the mass of the proton that we had earlier? 1.007, 1.01. Each proton is 1.01 and each neutron is 1.01. Electron is 0.0. Even if we go to the nearest hundredth, okay? 1.01 times 8, that's 8 protons. That's at least 8.08. And 1.01 times 8 neutrons would be 8.08. If you add those two, that would give you at least 16.16. Oops, I'm sorry, 10 neutrons, right? So times 10 neutrons. So that's 10.1. So 8.08 plus 10.1, that's already 18.1. That's already over 18. An oxygen 18 atom has a mass of only 17.991803. That's less than 18. That's less than the mass of 18 nucleons combined. Question? So this discrepancy is what you would call what's called the mass defect, okay? And Einstein gives us the relationship between this mass defect and the energy that you need to separate the particles. Okay, so in other words, by putting all of these things together, you get a stable atom, and in that process, for that atom to become stable, all of these particles must lose energy. So you have to put that energy back in to separate the particles. So the energy you need to split up the atom into the nucleus into its components is given by this equation, E equals mc squared. M is the mass, okay, the mass defect, and c is the speed of light, which is 2.998 times 10 to the 8 meters per second. So E equals mc squared. But for most of what we do in chemistry, we're just going to go to the second decimal place. We're going to be okay. You're not going to have to worry about the masses of the protons and neutrons not adding up. But it's just something that you should know, okay? All right. To the nearest tenth of an atomic mass unit, the mass of an atom is equal to its mass number. So if I asked you, what's the mass of magnesium-24? Well, you can look it up. It's going to be 23.9850423. But I would expect you to know that to the nearest tenth, that it is 24.0. If you round it, you'll notice if you round this off to the nearest tenth of a decimal of an atomic mass unit, 23.985 rounds off to 24.0. So if I were to ask you what's the mass of a carbon-14 atom, you should at least give it to me to the nearest tenth of an atomic mass unit. What is it? It will be 14.0. What's the mass of a carbon-12 atom? I'm sorry? Yes. 12.0. In fact, carbon-12 by definition is defined to have a mass of exactly 12 atomic mass units. That's the only atom that has an exact mass, okay? I'm sorry? Oh, okay. All right. Yeah, let's try that. Okay, let me pause. Let's try to see if we can get a better transmission. Okay, you want to log off for now and then log back in? All right, let's continue recording. So like I said, to the nearest tenth of an atomic mass unit, you should be able to give me the mass of any atom. Okay, whatever the mass number is, okay, that should give you the approximate mass of the atom. So carbon-14 would have a mass of 14.0 atomic mass units. And carbon-12, by the way, this is the only atom that's defined to have an exact mass. A carbon-12 isotope, okay, an atom of carbon-12 is defined to have a mass of exactly 12 atomic mass units. So that's a standard, so it's agreed upon. All the other atoms, to the nearest tenth of an atomic mass unit, it's whatever the mass number is, okay? So now, there's a number you'll see in the periodic table. You've probably learned of it as being called the atomic weight or the atomic mass. Okay, this is actually this number right here under magnesium, for example. Okay, this 12 is the atomic number. That's the number of protons, right? And the number down here, that's not the mass number. That is the average atomic mass or the atomic weight. Okay? So atomic weight is a unitless number that's typically shown in periodic table. That's the value of the average mass of atoms in a naturally occurring sample of an element. So in other words, if you have a naturally occurring sample of magnesium, some of those magnesium are going to be magnesium 24, some of them are going to be magnesium 26, okay? If you add up all the masses of all those atoms, divide by the total number of atoms, this is the number you get, 24.31. In other words, there isn't a single magnesium atom that has a mass of 24.31. Okay, that's the average for a collection of magnesium atoms. Most magnesium atoms would have a mass of either 24.0 or 26.0. It would be close to a whole number. All right, so if you look up the atomic masses of magnesium from webelements.com, you'll find that 79% of magnesium atoms in nature are magnesium 24. You'll notice the atomic mass of magnesium 24 is 23.99, or to the nearest tenth, that's 24.0 atomic mass units. The magnesium 25s are 25.0 atomic mass units, 24.99. Magnesium 26, 11% of the magnesium atoms you'll find in nature have a mass of 25.98, or to the nearest tenth, that's going to be 26.0 atomic mass unit. So how do you figure out the average? So if you have 79 of these, 79 times 23.99, right, plus 10%, so 10 times 24.99, plus 11% of magnesium 26, so 11 of those, 11 times 25.98, okay? You divide all of that by 100, that gives you the average atomic mass, okay? So you'll notice we can simplify this. You can say this is 0.79, 79 over 100 is 0.79. So 79% of 23.99 plus 10 over 100 is 10%, so 0.1 times 24.99 plus 11 over 100 is 11.11, so plus 0.11 times 25.98. So the way you calculate the average mass is you just multiply the abundance in percentage expressed as a fraction by the isotopic mass. This is the isotopic mass. Add them all up. Question? Is there still a lag? All right, so that's how you figure out the atomic weight that you see on your periodic table. All right, so let's talk about, all right. You can review this recording later, and you shouldn't see a lag since I'm recording it in real time, so over on this side, so there shouldn't be a lag when you see the recording later. Okay, maybe you think it will help if I slow down a little bit? All right. Now, electrical charge. All right. Electrons, how about, the audio should be okay, huh? Okay. Now, all right, let's talk about electrical charge. Electrons and protons are said to be electrically charged, and the unit for electrical charge is a coulomb, okay, capital C. And electrons carry the smallest magnitude of charge known, which is negative 1.6 times 10 to the negative 19 coulomb. So this amount of charge, we usually assign it a value of -1. So in atomic mass units, you can say that the charge, in atomic units, you say that the charge of an electron is -1. Protons have an opposite charge and equal in magnitude to that of an electron, but opposite. So the charge of a proton is positive 1.6 times 10 to the negative 19 coulombs, or we say it has a charge of plus 1. Neutrons, we say, are neutral. And so neutrons have a charge of 0. We say they're electrically neutral. Now, atoms, all atoms are neutral, electrically neutral. That means they're going to have the same number of protons and electrons. All right, so here's an example. An atom has 10 protons. How many electrons does it have? Very good. 10 protons, 10 electrons. Electrically neutral. All right. What's the nuclear charge of a magnesium atom? What do we mean by nuclear charge? That's the charge of the nucleus of a magnesium atom. And here's magnesium right here on your periodic table. What's the answer to this? How many protons in a magnesium atom? Okay, so 12 protons, they're all in the nucleus, right? And a charge of the proton is plus 1 for every proton, okay? So 12 times plus 1 is plus 12, okay? Or if you want it in SI, what would that be? You're going to say 12 times 1.602 times 10 to the negative 19 coulombs. That would be the charge in SI units for the nucleus of a magnesium atom, okay? But the magnesium atom itself has a neutral charge because surrounding that nucleus are 12 electrons. Now, particles with like charges, we say, repel each other. You've learned that in your early science courses, right? And particles that have unlike charges attract each other. These types of forces are called Coulombic forces, okay? And so this brings up a question: if protons, which are all positively charged, repel each other, why are they all in the nucleus, so tightly packed in that nucleus? The answer is that there's actually another force, an attractive force that only works at very, very, very short distances, like the distances within a nucleus. And this is called a strong nuclear force. And that counteracts the repulsions among the protons. So that's what's holding them in the nucleus. In addition, this strong force also involves the neutrons. And so oftentimes you're going to need neutrons to fully stabilize a nucleus. Okay? And so if you want to know more about the strong force, this is the website that you can go to. That's a good website to go to learn more about the strong force. So let's do a few clicker questions here. I think I have a few coming up. Which of the following subatomic particles are found in the nucleus of an atom? Question? Okay, so protons and neutrons, protons and electrons, neutrons and electrons, or protons, neutrons, and electrons? Hello? Can't hear you. Can you hear me? Okay, I think we have an audio problem. Okay, so 13 said A, 1 said B. All right, so very good. The answer is A, protons and neutrons. Those are what you'll find in the nucleus of an atom. Here's another clicker question. Among these elements, which has the most number of protons per atom? Is it beryllium, oxygen, chromium, or chlorine? I still can't hear you, so I might as well type your answer. Okay, so popular answer is C, chromium. All right, so beryllium atomic number is 4, so that's 4 protons. Oxygen has 8 protons per atom. Chlorine has 17 protons per atom. Chromium has 24 protons per atom. Correct answer is C. All right, here's another question. How many neutrons does an oxygen 18 atom have? Is it 8, 10, 16, or 18? So here's oxygen right here. Is it 8, 10, 16, or 18 neutrons? Okay, 2 said A, 9 said B, 2 said C, and 1 said D. Okay, so 9 said B. Popular answer is 10. Very good, because oxygen has 8 protons. If you have 18, that must be 10 neutrons. 10 plus 8 will give you a total of 18 nucleons. Okay. Symbol carbon-13 represents an atom with A, 13 protons, B, 13 electrons, C, 13 neutrons, or D, 13 nucleons. And here's C on your periodic table. So carbon's atomic number 6. Ten said D. Very good. 10 has 13 nucleons. That means of that, 6 are protons and 7 are neutrons for a total of 13 nucleons. Very good. Which of these has the largest mass number? A, manganese 56. There's manganese. B, iron 56. Or C, chromium 56. So here's chromium right here. Manganese is over here. Iron's over here. Which one is the largest mass number? A, B, C, or D? manganese 56, iron 56, or chromium 56? Okay, 8 said B and 6 said D. All right. What's the mass number? That's the number that you see on the upper left-hand corner, right? So mass number of iron 56 is 56. Mass number of chromium 56 is also 56. Mass number of manganese 56 is also 56. So they all have the same mass number. Okay, this time, which one has the most number of neutrons? Chromium 54. So chromium has an atomic number of 24. Is it manganese 54? Or is it iron 54? Here's iron and there's manganese right there. Okay, 4 said A, 9 said C. Okay, so we have a vote of 4 for this and a vote of 6 or 9 for this one. Let's see. They all have the same mass number, right? So protons plus neutrons is 54. Well, how can you have the most number of neutrons if you have the least number of protons? So which one has the least number of protons? So in the case of chromium, you have 24 protons. So 54 minus 24, that's 30 neutrons. So what's the correct answer here? Correct answer is, let's redo the poll. Okay, much better. So correct answer is A. Chromium 54 has the most number of neutrons. All right, let's see if you remember the masses. Which of the following has the largest total mass? 2 protons and 4 electrons, 2 neutrons and 2 protons, 6 electrons, or D, they all have the same mass. Okay, 13 picked B and 1 said C. Okay. So electrons, we say, contribute hardly anything to the mass of an atom. So of its three choices, you compare the first two protons, that's 2 times 1.0, so that's 2.0 atomic mass units. 2 protons and 2 neutrons, that's 4 nucleons, that's 4 times 1.0, that's 4.0. The correct answer is B. What was the popular answer? B. Very good. All right. Which of the following best describes how the mass of an atom is distributed? A, it's concentrated in the nucleus. B, it's evenly distributed throughout the space occupied by the atom. C, it's mostly due to electrons. D, it's mostly due to neutrons. All right, 8 said E. All right. Okay. So what's the answer to this one then? Mass of the atom is concentrated in the nucleus. All right. Here's another easy one, should be. The mass of one atom of magnesium-26 is closest to A, 24.3, B, 24.0, C, 26.0, or D, 12.0. Mass of one atom of magnesium-26 is closest to 24.3, 24.0, 26.0, or 12.0. Okay, 14 says C. Very good. So the mass number tells you what the mass of the atom is to the nearest tenth of an atomic mass unit. So you don't need to look up the answer in a periodic table because it tells you right there what the mass is of that atom. Okay, here, a little critical thinking involved. In a fictitious world, element X has only two isotopes, X77, which has a mass of 77, and X78, which is a mass of 78.0 atomic mass units. And the relative abundance of the heavier isotope is 30%, and so what's the average mass of X atoms? So if you had a periodic table in this fictitious world, what number goes as the atomic weight of element X? Is it 77, 77.3, 77.5, or 78? So it's 30% of the heavier isotope. Okay, I'll give you a little bit more time to work on it. All set B. Good. Let's see. All right. So 30% of the heavier isotopes, so the 78. If you had 10 of these, 3 would be 78. The other 7 would be 77, right? 1, 2, 3, 4, 5, 6, 7, and then 378s. Okay, so that should be close. It should not be 77. The average should not be 77. It should not be 78. It can't be 77.5 because that would be 50-50, half 78, half 77. So it's got to be 77.3. And the way you would calculate that is you're going to say that 30% would be 78. So 0.3 times 78 plus 0.7, 70% would be 77.0. Okay, and so that should give you 77.3. Okay, let's see if you remember what we meant by nuclear charge. Of these elements, which has the highest nuclear charge? Beryllium, oxygen, chromium, or chlorine? Okay, most said C. All right, correct answer is C. Very good. That's 4 protons. So that's a nuclear charge of +4. That's a nuclear charge of +8 for oxygen, a nuclear charge of 17 for chlorine, and nuclear charge of 24 for chromium. Correct answer is C. Okay, the rest of these you can skip. You'll probably see them in the homework. All right, so let's just move on to ions and molecules. As I mentioned earlier, for most everyday phenomena that you see around you, the nuclei of the atoms remain intact. So the nucleus doesn't change. But atoms, the way they interact with other atoms is through their electrons. So atoms may lose electrons to other atoms. An atom may gain electrons from another atom. And atoms may share electrons with other atoms. And so when atoms do this, what you get are called ions and molecules. Okay, so let's talk about ions. Ions can be classified as cations or anions. Cations are what we would call positive ions, and anions are what we would call negative ions. Cations are positive ions because they have more protons than electrons. So you can form a cation, for example, if an atom were to lose electrons. So you'd end up having more protons in the remaining ion. So a cation, we say, is positively charged. An anion has more electrons than protons, so anions have a negative charge. The charge is defined as just the number of protons minus number of electrons. So ions are formed by losing or gaining electrons. So if you end up with fewer electrons, they have a positive charge. If you end up with more electrons, then you have a negative charge. An example here, let's say I have an ion that has 12 protons and 10 electrons. So what's our charge? Number of protons is 12 minus number of electrons is 10. You have more protons, so the charge is positive 2. You have 2 more protons than electrons. So this is a cation. Every atom is electrically neutral, as we talked about earlier. That means equal numbers of protons and electrons. So the charge of an atom is 0. Now, if an atom loses or gains electrons, what you get is called a monatomic ion. Monoatomic, which is shortened to monatomic. So that's monatomic ion. And here's an example of a monatomic ion and how it's represented. When you see the symbol for magnesium, symbol for an atom, and you see a charge, you'll see the charge written on the upper right-hand corner. You're dealing with a monatomic ion in this case. So the charge is shown on the upper right-hand corner. The standard way of writing the charge is to write plus if it's just a +1. And then if it's more than +1, you put the number in front of the plus. Instead of writing +2, you write 2 plus. Instead of writing +3, you write 3 plus. Okay? If the charge is negative, you use negative, just a single negative sign, minus sign, or 2 negative, 3 negative, and so on. Now, in magnesium ion, as shown here, like magnesium with a +2 charge, there are how many protons and electrons? How do you figure this out? Well, magnesium automatically means 12 protons. Okay? So that means if the charge is +2, you have 2 more protons than electrons, so the number of electrons must be 10. 12 minus 10 is +2. So that means a magnesium ion, a magnesium that has lost 2 electrons, is what you would get if a magnesium atom were to lose 2 electrons. Okay? So magnesium loses 2 electrons. So now instead of, so you have originally 12 protons and 12 electrons, you end up with just 10 electrons. So 12 minus 10 would be +2. Okay, so here's your periodic table again, and here's a question. What type of monatomic ion is one that has 7 protons and 10 electrons, and what's its symbol? So what's our charge here? Number of protons is 7. Minus number of electrons, which is 10. Our charge is -3. So it's a negative charge, so that means it's an anion, a negative ion. And what would be its symbol? You go by the number of protons, 7, so you look for atomic number 7, there's nitrogen right there. So this is a monatomic ion that's derived from nitrogen. So a nitrogen atom with a charge of -3. So the symbol would be N3 minus. Okay? So you say this symbol means you have a nitrogen atom that has gained 3 electrons. You remember each electron carries a -1 charge. So a 3 minus means 3 additional electrons. So 3 more electrons compared to protons. Now, a molecule is what you get when 2 or more atoms are linked by covalent bonds. And a covalent bond is simply, covalent bonding simply means sharing of electrons. So a molecule is an electrically neutral species, we say. It has an equal number of protons and electrons. So what you have in the molecule are 2 or more atoms sharing electrons. Sharing of electrons is called covalent bond. Okay. We can specify what's called the formula of a molecule by just writing the symbol for each element present, for each atom that's present in the molecule. And you use subscripts to indicate how many atoms of each kind are present in the molecule. If you don't write the subscript, that is implied to be a subscript of 1. All right. So here's an example. 20% of the molecules in the air we breathe are O2 molecules. So how many atoms are there in one molecule of O2? That subscript of 2 means you're dealing with a pair of oxygen atoms in a molecule. So a pair of oxygen atoms. So most of the atoms of oxygen you'll find in nature are paired up. Okay. So in the air that you breathe, the oxygen atoms are paired up. So we refer to oxygen in the air we breathe as O2. They're made up of O2 molecules. The 2 oxygen atoms are sharing electrons. So here's a question. Which of these represents a molecule? I'm sorry. How's that? Okay, so this is symbol for an element called cobalt. That's not a molecule, okay? A molecule should have at least 2 atoms. So the total subscript must at least be 2. So CO means this is carbon with a subscript of 1. Oxygen has an implied subscript of 1. So this would be the symbol for a molecule, CO. That's carbon monoxide. That's the gas that kills you if you run your generator in your garage, or if you lock yourself in your car in your garage. Okay. Here's another example. How many atoms are in a molecule of acetic acid? And the formula for the molecule is CH3COOH. Let me see what the class's answer to that is. CH3COOH. How many molecules? How many atoms are in that molecule? 8. Let's see. So the subscripts are 1, 3, 1, 1, 1, and 1. So 1 plus 3 plus 1 plus 1 plus 1 plus 1 plus 8. Okay. Of those, 2 are carbons. 2 carbons. Oops. 2 carbons and 4 hydrogens. That's 3 and 1. That's 4. And 2 oxygens. So you could have written the formula for acetic acid molecule as C2H4O2. As we shall see later, there are reasons why it's written this way, and it has to do with how the atoms are connected in the molecule. Okay, here's a question. How many protons and electrons are in one molecule of ammonia? So you have to go back to periodic table. Nitrogen has an atomic number of 7, and hydrogen has an atomic number of 1. How many protons and electrons are in one molecule? Let's see what the answer is. Ten protons, 10 electrons. Very good. Okay. So you have each nitrogen has 7, each hydrogen has 1, so it's 1 times 3, that gives you 3, so 10 protons all in all. Since a molecule is neutral, you should also have 10 electrons. Now, a polyatomic ion is an electrically charged group of 2 or more atoms sharing electrons. So you can think of it as a charged molecule. And just like a molecule, your formula has subscripts next to symbols for atoms, telling you what atoms are there and how many. And just like a monatomic ion, it should have a superscript to indicate what the charge is. So for example, how many protons and electrons are in one nitrate ion? Well, there's one nitrogen atom that has 7 protons. 3 oxygen atoms. You have oxygen has 8 protons. Okay, here's nitrogen with 7. So 8 protons times 3, that gives you 24 protons. So 7 plus 24, that's a total of 31 protons. Okay? Now, you'll notice here there's a negative charge. That negative means 1 extra electron. So the number of electrons is 32. So 31 protons minus 32 electrons, that gives you a negative 1 charge. Okay? What time are we supposed to stop? It's 9:05 by my watch. Is it about time to go? Okay, what's the schedule like? Okay, so we still have, we end like at 9:10? Yes, it's on Moodle. The lab's on Moodle. It's actually a computer lab, so I don't know if you'll have access to the lab. All right. Okay. Hopefully things will be better next time. All right. Okay, thank you. I'll see you Thursday. But I'll be around tomorrow if you need anything, you need any help. Okay, bye.